So, as I discussed about the polar solid, right. So, it has permanent dipole moment. So, atoms or ions or molecules of these materials are having permanent dipole moment. Now, that dipole moment we have seen that dipole moment, this polarizability due to the orientation or dipolar polarizability that depends on temperature, right. So, so what we have seen that polarizability orientation, that is a mu square by 3 kBt, right, mu square by 3 kBt, and mu equal to E into this. So, you have to multiply E. Okay. Now, forget this for the time being, this expression of this things, just what I want to tell you just qualitatively. So, this you have material which are having the dipole moment, it is just similar to the magnetic material. This polar dielectric material is similar to the magnetic material. Okay. Magnetic material, it is paramagnetic or ferromagnetic or antiferromagnetic, right. So, whatever the magnetic material having the permanent dipole moment, not induced dipole moment, permanent dipole moment, they are showing this different kind of magnetic property, different kind of magnetic materials, ferromagnetic, antiferromagnetic, etc. So, here also that's the way these polar solids are classified. So, it is the pyroelectric, it is the ferroelectric, is the antiferroelectric, okay. And there are some more types, it is and very useful for device application. So, that is the, it is called piezoelectric, P-I-E-Z-O, piezoelectric, and pyroelectric, P-Y-R-O, pyroelectric. Okay. So, here whatever this pyroelectric, ferroelectric, antiferroelectric, these three are just same as that the magnetic material. Okay. So, there will be pyroelectric to ferroelectric to pyroelectric phase transition, that is also similar to Curie-Weiss law. Okay. To explain this ferroelectric, so here we consider in case of paraelectric, as I told earlier, whatever, that is basically paraelectric, paramagnetic gas. So, dielectric gas, as I mentioned earlier. So, basically that is paraelectric gas. There is no interaction in the dipoles, among the dipoles in this material. Okay. So, just like gas. So, now when we consider the interaction, so you remember this mean field approximation or Weiss field. So, similar interaction if you put here. So, you will that same way, there is no difference, same way one can be able to show C by T minus T C for this ferroelectric material. Okay. And in ferroelectric material domains are there. So, origin of these things, just the interaction of these electric dipoles. Okay. So, the different kinds of materials are there. So, this so just I will, so since they are similar, so I will not describe more on that topics. So, same way as we have described in magnetic metal, the same way one has to describe. Okay. So, I am interested to tell more about this piezoelectric and pyroelectric just qualitatively. So, what is piezoelectric? Piezoelectric is dielectric material. So, this piezoelectric, piezo means pressure, pressure, stress. So, some dielectric materials are there. If you put pressure on them, then it is polarized. This material is polarized. Okay. Okay. So, this type of materials is called piezoelectric material. Okay. Or just reverse one, if you stress means how to produce stress, okay, pressure, then its materials dimension will change if you apply pressure. So, basically due to change of dimension, this polarization occurred, okay, and that polarization occurs means then basically you are getting in terms of voltage, that polarization, that charge, you are getting charge basically. So, that you can get in terms of voltage, in terms of electric field. Okay. So, here this type of material we use to express to get the electrical signal from the stress. So, stress can be mechanical stress, it can be converted into electrical signal because of the stress we are getting, it is material is polarized. Okay. So, this so just reverse on. So, you are getting say electrical signal, you are getting voltage. Now, if we apply the voltage in this material, then its dimension changes. Okay. If you change the dimension, then you will get electrical, this material is polarized, you will get electrical signal that can be clearly in terms of charge or voltage, okay, not current in case of dielectric material. So, getting say voltage. Okay. So, now if you apply, so pressure is giving voltage, now if you apply voltage, then it will give pressure. So, due to it, this metal will feel pressure. So, due to feel stress, it feel force, and due to that it will change its dimension. Okay. So, that metal is used to measure the displacement, in nanometer order, So, we tell is piezo drive means this using this dielectric piezoelectric material, one can displace any object, putting on that material, displace this object in nanometer scale. Okay. So, that is the great application we use in our laboratory generally when we need displacement of this order of nanometer, okay, even less, even maybe angstrom. So, this atomic force microscopy, magnetic force, that is STM, scanning tunneling microscope. These are the microscope. Using this microscope, we basically image this image of material, and this in atomic resolution. It's not really atomic resolution, but its resolution is less than nanometer, less than 1 nanometer. Okay. So, we can take image on a surface of this material, and we can see the arrangement of the atoms on that surface or in this material. Okay. So, now you need something to move, okay, because you are scanning. So, scanner has to move, okay, in nanometer scale. Okay. So, how to move? So, there we use this piezoelectric material. So, we apply voltage. So, on this piezoelectric material, and then piezoelectric material changes dimension, and so then it moves, the scanner moves. So, scanner set on this piezoelectric material, it is taken in shape of cylinder basically, and then it moves. Okay. So, applying voltage on this piezoelectric material, so our scanner moves and it takes the image of this surface. Okay. So, these are very useful for very fine movement in nanoscale. So, this is the one type of dielectric material and very useful for device. And pyroelectric material, pyro means I think temperature, pyro is basically temperature. So, if you change the temperature of the material, then it is polarized, this material is polarized. Okay. So, there are some dielectric material, if you change the temperature of this material, so it is polarized. Okay. So, then again here this material we use that as a temperature sensor to measure the temperature, basically high temperature, when you are temperature of this say few thousand degree centigrade. So, in that case, so this type of material is used as a temperature sensor, and we measure the temperature. So, this material is temperature sensitive. When temperature changes, then it is polarized. Okay. Means again it is giving me charge or voltage, electrical signal. So, temperature is converted into electrical signal. Okay. So, that is the pyroelectric material. It is dielectric, but type again classified as a pyroelectric material. This material is sensitive to the temperature. Okay. So, yeah, just I am telling you definition, because I will not describe more, because already this course is I have taken lot of classes and I have to finish, otherwise it will be heavy for you. So, and that is for undergraduate level, that is good enough. So, this ferroelectric, now ferroelectric material is a dielectric material. So, dielectric there are different kinds. So, among polar solids, so these are the different types. Okay. Okay. So, ferroelectric material is, if this for ferroelectric, for piezoelectric, for dielectric, for these three types of material. So, one condition is required, that is this it's very sensitive to the structure of the material, very sensitive to the structure of the material. So, generally we tell this it is symmetric material or non-symmetric, non-centrosymmetric material. Okay. So, this symmetric we express in terms of rotation. So, this material has to be ferroelectric, to be piezoelectric, to be pyroelectric, it has to be non-centrosymmetric. It has to be non-centrosymmetric. Symmetric means a rotational, with respect to rotational symmetry. So, there is symmetry. So, non-centrosymmetric. So, I will not explain. So, this it is just I want to say this very structure sensitive. Okay. So, among pyroelectric or piezoelectric, whether it is ferroelectric or not, or they are okay, vice versa. Okay. So, it just I want to clear it. So, reality is there are 21 classes of non-center symmetric, 21 classes of non-center symmetric material, 21 classes of non-center symmetric material. Okay. So, this 21, out of this 21, it is telling 20 class of non-center symmetric material are this piezoelectric type, and then out of this 20 class of non-center symmetric material, only 10 class of non-center symmetric material are pyroelectric. Okay. And now, out of these 10 class of non-center symmetric materials, all are not ferroelectric, some of them are ferroelectric. So, what is the condition to be ferroelectric? So, non-center symmetric, it is not the only condition. Condition to be ferroelectric condition is that this dipole moment, permanent dipole moment, whatever this metal is having, so its change is orientation with respect to magnetic field, electric field. Okay. If this polarization, if this dipole moment is changeable applying electric field, if its direction can be changed applying electric field, then only it is called ferroelectric material. Okay. Now, it is ferroelectric, it is similar to ferromagnetic. Okay. So, it has hysteresis loop, right. So, these are called this P versus this electric field, So, this remanent polarization, saturation polarization, coercive field, the coercive electric field. Okay. So, the same way we express. So, I think I will not discuss about these things more. So, these are the overall idea I could give you about this dielectric material, and these three are very important for application. Okay. And since these are very similar to the ferromagnetic material, so one can understand from the same concept, and these two are very important for device purpose, that just I told their definition, and this way I just told you that how. So, applying electric field, the dipole moment, direction of dipole moment of all metals is not possible to change. Okay. So, there are very few materials, dielectric materials are there. So, there these dipole moment are changeable with the electric field. Okay. So, now I will tell you about the, just briefly I will tell some few statements or few definition of superconducting materials. So, I will just briefly tell about the superconductivity. Okay. So, superconducting material, so you must have heard this name, and it is very important for application, but unfortunately it is observed only at low temperature. Only observed this superconducting property of materials at low temperature. How low? What is the, as I told in science, one has to define the parameter. It is not high, small, low is not very effective. So, basically this how we get the, how we can reduce the temperature of a body. So, that basically we use liquid helium. So, liquid helium, that temperature is basically 4 Kelvin, probably I told you earlier. So, this is the 4 Kelvin. So, this superconductivity first it was discovered at 4.2 Kelvin of mercury, Hg, mercury. Okay. When the resistivity of this mercury was measured, resistivity of this mercury was measured as a function of temperature. So, its behavior was, so it was changing, it was changing. So, when temperature is decreased, then it was changing like this, and then suddenly it jumps, it comes to the zero resistivity. Okay. So, this the observation first was made by, I think this what is name this Kamerlingh Onnes in I think in 1911. That was first observed in 1911. Yes, Kamerlingh Onnes, he observed this type of behavior of resistivity as a function of temperature. Okay. Because we know this for normal metal, if it is pure, generally this temperature varies. If it is pure, temperature its resistivity varies linearly like this. It is not all the time linear. So, I think it is maybe I think lower temperature it is like this, I think variation like this, but this if the material is impure, then its variation its variation is like this, because there in that impure material there is a residual resistivity rho 0, right. So, that was the behavior of normal material, normal metal, I can say metal, but suddenly this was observed and this resistivity is 0. So, this behavior is basically is called the superconductivity, and this temperature here, where below this temperature it is the resistivity is 0, resistance of this material is 0. So, that temperature is called critical temperature. Below this critical temperature it is different state than the normal state of metal. So, then we tell this normal state of metal and superconducting state of metal. So, below this temperature, this new state of metal where resistance is 0, that we tell superconducting state, and above this temperature it goes to this normal state. So, there is a phase transition at this temperature from superconducting state to the normal state or normal state to superconducting state. So, but it is not the only condition that this when resistivity will be 0, then it is superconductor. Most important property of superconductor, I think its more useful, more authentic characteristics of superconductor is the magnetic property of the superconductor. Superconductor is a diamagnetic. Superconductor is a diamagnetic. Superconductor is a diamagnetic. Right. So, that is there is a Meissner effect, this very nice effect or discovery, that say if you have taken a material, okay, now put in put in a magnetic field, put in a magnetic field. Okay. Now, you are changing the temperature, you are changing the temperatures of this material. Okay. So, now this temperature here in this case it is greater than Tc, that means it is at normal state, it is at normal state, this metal is at normal state. Okay. Now, if you decrease the temperature and come the T is less than Tc, come T at less than Tc, then it becomes superconductor. It will tell it is superconductor if we find this type of yes. Yes. So, if we find this type of change of magnetic field. Okay. So, in this case magnetic field is passing through this the material okay, when temperature is less than Tc, and when temperature is less than here greater than Tc, when it is less than Tc, then this magnetic material magnetic field is not passing through this. Okay. So, this is perfectly diamagnetic, it is perfectly diamagnetic. Okay. In case of diamagnetic, you know this magnetic field cannot penetrate this diamagnetic material. Okay. So, in case of diamagnetic, what happens? So, you know this B equal to mu 0 H plus m. Okay. Now, here B 0 is 0, inside the material what is the flux density? Okay. That is 0. So, B this is equal to 0, this is equal to 0. So, obviously, H equal to minus m. Okay. So, when you will draw the magnetization as a function of magnetic field, what you will see? Here I have taken negative sign. Okay. So, if you will see this type of change. Okay. So, keeping this at temperature, it is less than Tc, but if you bring this temperature at T equal to 0 is 0 Kelvin. It is not possible to go to exactly 0 Kelvin, but close to the 0 Kelvin. So, but for definition I have to tell that when temperature is at 0 Kelvin, then you will see that it is changing, you are changing the magnetic field. So, its magnetization minus m is changing linearly, right, they have linear relation. So, then suddenly what happens? So, after that magnetization becomes 0, okay, it drops. Okay. So, this case here, what happens? So, there is a critical field, for superconductor when temperature is T equal to 0, and this is the highest magnetic field AC critical field. Below these critical fields it's diamagnetic, and above this critical field it is not diamagnetic, because it is not following this curve, this straight line, but suddenly it stopped, drop. Okay. So, then we tell that this superconducting material is superconductivity is destroyed by magnetic field. Okay. So, it goes to, for superconducting state, to the normal state. Okay. So, AC is the critical magnetic field. Below of this critical field, the material is in superconducting state, and above this critical field it goes to the its phase changes and it goes to the normal state. So, not only temperature is important. Okay. So, generally we define in terms of temperature, but it is not only temperature is important, but this magnetic field also important, because magnetic field destroy the superconductivity. Okay. So, now interesting things is that this superconductor is basically can produce the highest magnetic field, so far in our laboratory. Using electromagnet we get just hardly 2 to 3, maximum 2 to 3 Tesla, but using these superconductors in our laboratory we get 10 to 20 to 30 Tesla. Okay. So, but this critical field generally for most of the materials, okay, we see that it's very less than 1 Tesla. Okay. Say few millitesla. So, it is less than 1 Tesla. Okay. So, if we apply magnetic field above 1 Tesla or this field, okay, so it will not be superconductor, it will lose the superconductivity. So, then how this superconductor is producing the maximum like 10, 20, 30 Tesla field. Okay. So, that is the question. So, I will answer of it. So, to answer of this question, so basically we have to classify it. So, this effect, diamagnetic effect, whatever observed, okay. So, this called Meissner effect, Meissner effect. Okay. And this is the very authentic test for superconductivity, that it has to be diamagnetic. It is not only rho equal to 0, it is not the sufficient condition, it has to be diamagnetic. So, then there is a again critical field. Now, this, so this the two types of, so we classified the superconductor into 2 types. So, one is called type 1 superconductor, one is called type 1 superconductor, type 1 superconductor, okay. So, type 1 superconductor which follows this. So, its critical magnetic field is AC, which follows this. Okay. So, AC one can write, so generally I prefer to write BC, I prefer to write BC. Okay. Oh, AC also one can write anyway. So, when it follows like this, so then it is, we tell this type 1 superconductor, but there are some materials where it follows like this. Okay. So, after coming here, so then from here it starts to decrease. Okay. It does start to decrease. So, it does not follow this one, it does not follow this one. So, it does not follow this one. Okay. So, then this the one critical field, this is another critical field. Okay. So, this we tell if it is H BC1 and this BC2. Okay. Now, so if some materials, if it follows this type of behavior minus m versus this magnetic field, if follows this type of behavior, then we tell this is the material is superconductor, type 2 superconductor, type 2 superconductor. Okay. And basically type 2 superconductor is responsible for this higher magnetic field from superconductor. Okay. So, how that I will explain how we are getting higher magnetic field in this from this type 2 superconductor. So, here you see this. So, this type 2 superconductor, I think, yeah. Okay. So, here what is happening? So, instead of it, so this change is like this. So, it is following this type 1 superconductor curve, but here instead of coming to 0, it is decreasing like this. Okay. So, it is decreasing slowly. So, this part, so this we can tell this the purely, we tell this purely this superconducting state, this purely superconducting state, and in this region we tell between BC1 and BC2, in this region its superconducting state, it is decaying. Okay. So, that means that is the, so something is growing, so normal state is growing. Okay. So, then between these two, this part, okay, so this part we tell the mixed state, we tell mixed state. Okay. So, above BC2, that is the normal state, above BC2 this is the normal state. Okay. So, this is the mixed state. Okay. So, mixed state means the superconducting state as well as this superconducting state as well as this normal state are there. Okay. So, now very interesting event, if you take a type 2 superconductor or if you take a superconductor, so say in cylindrical form. Okay. In cylindrical form. Okay. Now, put in magnetic field, and when and apply magnetic put in magnetic field and change varies the magnetic field. So, when its magnetic field B is less than BC, okay, less than BC. So, if it is type 2 superconductor, so I can write less than BC1. So, it is the pure superconducting state. So, you will see the magnetic field, change of magnetic field as we have seen, like just diamagnetic case. Okay. Okay. Yeah. So, as if it repels from this. Okay. So, no field will be through this, through this. Okay. Now, if your field is if your field between B is greater than BC1, but less than BC2, then what will happen? then you will see what you will see? You will see that as I told this, it is mixed state, it is mixed state. So, it has, so this has superconducting phase as well as that normal state, normal metal. So, here interestingly, so this magnetic field, so if it is how they arrange normal state and this superconducting state, both are how they are arranged here. Okay. So, here basically this normal states, okay, they form a column, basically they form a column, okay, they form column, basically column wise there, if it is, this is the shape of the material. Okay. Now, your now magnetic field, these are the, you see this column only this normal state, column is only normal state. So, now your magnetic field will pass through this, magnetic field will pass through this, okay, and it will, of course, it will pass. Okay, it will pass through this. So, basically, okay. So, now these are called vortex, these are called vortex, okay, these are called vortex. And the interesting thing is that this through this vortex, okay, through this vortex, the how much magnetic field will pass through it. Any amount of magnetic field cannot pass through this. So, this field is only the amount of magnetic field pass through it, the flux pass through it, that is phi 0, that is phi 0, and interestingly it is equal to 2E, phi 0 equal to H by 2E, okay, and they are constant. And then this value, if we put 2.067 into 10 to the power minus 15 Weber meter, Weber, okay, Weber. Okay. So, this vortex, this the normal state of the material, their size or they are arranged in such a way. Okay. So, only this amount of flux will pass through that. Okay. So, how much flux will pass through these superconductors in case of type 2, in case of in mixed state. Okay. So, that depends the density of the vortex. Okay. The density of the, yes, I think that depends on the density of the vortex, and if the density of vortex is n, so total flux will pass through it equal to n phi 0. Okay. That is nothing but magnetic flux, magnetic induction B, right, because per unit area what is the flux, that is the magnetic. So, that is basically passing through this material. So, now imagine that this superconducting material is type 2 material, and in this range it has this kind of vortex. Okay. Now, this material is sensitive, it is selecting it is allowing that this tiny amount of the flux through it. Okay. So, this material is sensitive, can sense to this very tiny flux, very small change of magnetic field. Okay. So, that superconductor is very is in our laboratory we use to detect the flux, okay. And that is the basically in case of SQUID. In case of SQUID, that is the on magnetometer superconducting SQUID, superconducting quantum interference device, superconducting quantum interference device SQUID. Okay. In SQUID we can measure the change of magnetization. So, change of magnetization in terms of flux, you will get the magnetic field or flux, and using these superconductors we can measure the change of the flux. Okay. There basically we use this, it is called Josephson junction, probably I will tell you about that one. Okay. So, this is the very interesting phenomena of superconductor, type 2 superconductor. Okay. And this type 2 superconductor is used for producing the magnetic field, very high field, because this BC1 is very small, but BC2 of some metals is very high, even 100 Tesla. Okay. BC2 of some metal is even 100 Tesla. Okay. So, because of this high field, so below of this field we can use superconductor. So, it will remain superconductor, although it is in mixed state, but it is sufficient for our purpose to produce the magnetic field. If it is purely superconductor state, then if you put current once in this loop, then there will be no loss. Okay. All the time current will pass through it, and you could get magnetic field from that current in a loop. Okay. But since it will be in mixed state, so there will be some normal state also, there will be some resistance. So, there will be energy loss, but this helps us to get very high field. So, there are many things in superconductor, but yeah, I think another part is Josephson junction. Just I will tell about the Josephson junction, and this any flux, this basically called the flux quantization, you know. It is the flux quantization is just similar. If you take a ring of superconductor and then passing through this, how flux pass through it, okay, through inside the superconductor. If you take this ring of superconductor, how flux pass through it, So, this flux basically any flux cannot pass through it. So, it is quantized, this flux is quantized. Okay. So, only this amount of flux phi, it has to be n times of phi 0, and that is the phi 0, Okay. So, this control is in this order, you know, phi 0, and this value is this. So, that is why it is very sensitive to this magnetic field. Yes. So, then another interesting phenomena is basically the Josephson junction. Okay. So, basically two superconductor is separated by a two superconductor, this is one superconductor, this is one superconductor separated by insulator, okay. Then this is called Josephson junction. And interesting is that without applying any voltage, electric field, so there is a current through the junction, and so that is called the DC Josephson junction. DC Josephson junction. DC Josephson junction. Okay. So, without applying any voltage, if we get current through the junction, then it is called the DC Josephson junction. Now, if we apply DC voltage, across this junction, then you will get current, AC current. You will get AC current through this junction, and frequency of this AC current is 2eV by H, 2eV by H, again here H by 2e or here 2e by H and times V. Okay. So, that will be the frequency. Very interesting, applying DC voltage, but getting AC current through this junction. Okay. So, that is called AC Josephson junction, Okay. And this Josephson junction, basically the two Josephson junction is used in this magnetometer, SQUID magnetometer. Okay. SQUID magnetometer. So, if you this two SQUID, it's okay. Now, it is the basically two okay. So, two junction. So, here you are putting through this, you are putting just passing current through it, and here current is going out. Okay. So, current will come here and this one current will flow through this junction. This is a J1 and another current will, this other part will okay, through the junction. The junction, this thickness of these two are different. Okay. So, when current pass through it, so that J1 is basically J0 and then yeah. So, depends on the phase difference, phase of current at this side at the beginning and this phase of the other side. So, there will be phase difference between this both side, okay, between this current of these two sides. So, this really is, its behavior is like that, delta 1 from junction 1. So, this phase difference is delta 1. So, J2 is basically J0 sin delta 2, here phase difference is delta 2. Now, here total current, your total current is J, no, this total current is J equal to J1 plus J2. Okay. So, if we add them, sorry, okay. Now, if things are in magnetic field, you know, if it is in magnetic field, so if there is no magnetic field, then this is the phase change, this there. So, if it is magnetic field, there is a phase, additional phase added. So, that is E phi by H cross C E phi by H cross C, and this is same, but it is minus, this is plus. Okay. So, total will be j equal to j1 plus j2. If we add them, it is basically, you see this, we are, this change of phase, this and now if we add them, the superposition of these two, we give this interference, and that interference, it is the interference is basically two light interference because of the phase difference, right. So, here you will get basically this current, whatever total current you will get, let us see, we will get the interference, okay. And that interference, that current, you can find out that 2 times of J0 and this some sine term and cos term, one can just find out, I will not write. So, that current will depend on this term, it will depend on this term. So, this current will depend on this flux, magnetic flux magnet. Okay. So, if you are measuring magnetization, so changing magnetization means changing the flux. So, these things is there. Okay. So, it can detect the change of this flux, okay, which is coming from magnetization. So, change of magnetization we will get in terms of change of flux. When flux will change, we will get this change of this current. And that current change, one can just from here, one can show this current change like this, maximum minimum kind of things. Okay. Okay. So, that is why we tell this instrument SQUID, superconducting quantum interference device. It is nothing but this is there. Okay. And this current, their magnetic field is produced that to this, if you take the solenoid of superconductor type 2 and this ring, and you pass current through it, and you will get current in a ring or in a solenoid. Okay. It will give you magnetic field, right. So, that as the normal procedure. Okay. But so, here one can, because there is no loss of, mainly there is no much loss of current. Okay. So, you can apply huge current in the, you can set huge current, okay, without voltage, or with small voltage you can set huge current in this loop, okay, and then you can get huge magnetic field, and that has to be less than Bc2, otherwise it will destroy this superconductor. Okay. So, this is the way we produce the magnetic field using superconductor. I think this is just without telling, just qualitatively I try to tell you without using any expression and the theory to understand the superconductivity. Superconductivity has gap, Cooper, Pierce. Okay. So, everything whatever I discuss, everything is derived from the theory, it is called BCS theory, Bardeen, Cooper and Schrieffer. So, BCS theory. So, that I think it's you do not need for undergraduate student. So, this is just overall what is superconductivity, what are the main properties of superconductivity, just I give you just rough idea about it. So, I think I will stop here and I finish this course. It is already I think 75 lecture or 76 lecture. So, I think it is better not to tell more about the things, then this course will be heavy for you, for undergraduate student. So, I think you have to wait for the higher study to learn more about these things. So, thank you for your attention. I will stop here.